Hello everyone, this is Jesse Crawford with New York Medical College, and this is going to be the supplemental lecture for correlation and regression. Regression is a technique that you use if you want to find a mathematical relationship between two variables. More specifically, if you want to find an equation that you can use to predict the value of one variable based on the value of one or more other variables. And this is also related to the concept of correlation. Let's say you're teaching a course, perhaps a biology course, and you're trying to investigate the different factors that play a role in student success in your course. And one thing you're interested in is the relationship between students' attendance and their overall course average at the end of the semester. So one thing you might do is take a big data set. This is a data set for 100 different students, and we have a scatter plot of course average versus attendance. So what that means is we take each individual student and we look at that student's attendance and that student's course average as an ordered pair, and then we plot that ordered pair on this graph. So you can see this graph actually shows us that we have pretty much an increasing relationship between attendance and course average. Those students who attend class more often tend to get higher grades in the course, and those who attend less often tend to get lower grades. So looking at this entire data set can be pretty messy, and what we'd really like to do is simplify it to a simple equation that just relates the course average to the attendance. And this brings in the concept of a regression line. So the regression line is just the line that fits that data set as well as possible. It's the line that in some sense minimizes all the distances from the points to the line. And you can see here that we did find that line. We can use a computer to find that line for us, and the computer can actually tell us the equation for the line. So here it says course average is negative 99.04 plus 4.22 times attendance. And one of the nice things about finding a regression line like this is that we can use it to make predictions. So let's say we wanted to predict a student's average based on their attendance, and we're looking at maybe one student attended class 40 times, a different student attended class 44 times, and a third student attended class 37 times. And we want to predict the course average for each of these students. Well, we have the equation from the previous slide, so we can just plug those attendance numbers in. So for example, for the student that attended class 40 times, we'll just take that 40 and plug that in for attendance. We'll perform that computation and we get a predicted course average of 69.76. That doesn't actually mean that that student will have a course average of 69.76, but it's our best prediction based on the data that we have available to us. And then you can see that we've repeated that process for the other two students as well. And we're seeing that the student who attended class most is most likely to have the highest course average, and the student who attended class the fewest times is likely to have a low course average. This slide shows a bit of terminology that's related to linear regression. First of all, we have two variables in this equation, course average and attendance. Now, from an algebra course, we would probably call attendance the input variable and course average the output variable. In regression, it's more common to call the input variable an independent variable and then to call the output variable a dependent variable. The idea being that you kind of think of the input variable as something that's independent, doesn't really depend on anything, whereas the output variable, the value of that depends on the value of the input variable. So you kind of think of the output variable as being the dependent variable in that case. Some other terminology that's used sometimes is to call the input variable the explanatory variable. So you might say that attendance here is the explanatory variable because it's the variable that's explaining what's happening to course average. And then you might call course average the response variable because it's the variable that's responding to the value of attendance. A couple of other important terms here are just what do we call these numbers in the equation? Negative 99.04 is the intercept, so from algebra we're familiar that that number is the y-intercept of the equation, and then the number that's next to the variable attendance is the slope. Now that we've seen an example of linear regression, let's take a look at the concept of correlation coefficients. The correlation coefficient between two variables is a number that basically measures how strongly related those two variables are. The notation that's typically used for correlation coefficients is the Greek letter rho, which kind of looks like a p. Now, the correlation coefficient is always between -1 and 1. If the correlation coefficient is equal to 1, then that indicates a perfectly linear relationship between x and y. And it's a positive relationship. That means if x gets bigger, then y is going to get bigger. If the correlation coefficient is equal to -1, then that's also a perfectly linear relationship. But it's a negative relationship. If x gets larger, then y will get smaller. And finally, if you have a correlation coefficient near 0, that indicates either a weak relationship, where there's basically not a very strong relationship between x and y at all, or possibly there is a strong relationship, but it's not linear. And we'll see an example of that in a moment. Here's our first example of a correlation coefficient. In this case, the correlation between the two variables is equal to 0.9. Now, whenever the correlation coefficient is close to 1, that indicates a pretty strong relationship, and it's a positive one. So if x increases, we expect y to increase quite a bit as well. And you can see that in this diagram. Another way to think about it is the scatter plot is pretty tightly packed around this line. So that again shows that there's a pretty strong relationship between the two variables. This is the opposite scenario. Here the correlation between the two variables is -0.9. Since this is so close to -1, we still have a strong relationship between the two variables, but it's a negative relationship. Whenever x increases, y is going to decrease. Again, the scatter plot is pretty tightly packed around the line because there's a pretty strong relationship between the two variables here. In this example, the correlation coefficient between the two variables is 0.06, which is really close to 0. And you can see here that there's really not a very strong relationship between x and y. You can have the value of x increase, and you really can't even predict what's going to happen to y. There's just not a very strong relationship here. So this is a good example of whenever you have a correlation coefficient close to 0, it could indicate that there's really just not a very strong relationship between the two variables. Now, before proceeding further, I'd like to talk a little bit about what the relationship is between correlation and regression. Well, it turns out that the correlation coefficient can be used to calculate the slope in the regression line. So let's take a look at this first equation on the slide. It says the regression line is y equals a plus bx. So this is what every simple linear regression line looks like. You've got the input variable, which is x, you've got the output variable, which is y, you have the y-intercept, which is a, and you have the slope, which is b. So it turns out that, yeah, the correlation coefficient can be used to calculate the slope. B is equal to rho times sigma y over sigma x. So in other words, if you take the correlation coefficient and you multiply that by the standard deviation of the output variable divided by the standard deviation of the input variable, that will actually allow you to calculate the slope of the regression line. Now, an interesting consequence of this is that if the correlation coefficient is 0, then the slope of the regression line is also 0, and vice versa. If the slope of the regression line is 0, then the correlation coefficient also has to be 0. Here we have an example of a data set where it's really not appropriate to try to fit a linear regression line. Now, the equation that was actually used to generate this data is y equals x squared. So it's not a linear relationship, it's a polynomial with an x squared term in it. In other words, it's a polynomial of degree 2. Another thing you could say is it's a quadratic polynomial, or you could say that this is a parabola. But in any case, this is not a situation where linear regression should be used. Now let's say that for whatever reason you did fit a line to this data set. Well, it turns out you would get a horizontal line. That's the line that does the best job of fitting this data set. Since the line is horizontal, the slope is 0. And as we saw in the previous slide, if the slope is 0, the correlation coefficient has to be equal to 0. So if you're a researcher and you didn't take the trouble to actually investigate this graph, you might calculate the correlation between x and y and say, oh, there's no relationship between x and y because the correlation coefficient is 0. But that would be incorrect. There is a relationship between x and y. It's a very strong relationship, but it's not linear. So to make a long story short, if you have a correlation of 0, it could indicate that there's a weak relationship between x and y, but it could also be the case that there is a strong relationship between x and y, but it's not linear. And that's why it's always important to take a look at a scatter plot between two variables before drawing any conclusions about the relationship between them. By the way, I'll just mention that the textbook has a lot of other important examples of different pitfalls that you can run into with the correlation coefficient. And I'd highly recommend that you take a look at those examples as well. So if we're not supposed to fit a linear regression line to this scatter plot, what should we do? Well, it is actually possible to perform polynomial regressions or other types of regressions that use different types of curves other than just straight lines. And that's what we could do here, and you can see that we get a line that fits the data really well. This isn't really a topic that we're going to discuss in this course, but I just wanted to let you guys know that this is something that you can perform, and it's really not too difficult to do so. Okay, let's take a look at multiple regression. Sometimes you don't just want to find the relationship between one input variable and one output variable. Rather, you might have several different input variables that you want to use to predict the value of an output variable. So going back to our example where we're teaching a course and we're trying to find the variables that impact student success in that course, let's say that we've decided to not just look at attendance, but to also look at high school GPA and SAT score and try to use all three of these variables to predict the course average in the course we're teaching. I'll remind you that the terminology that's commonly used in regression is to call the output variable the dependent variable and the input variables the independent variables. So in this case, our dependent variable would be course average and our independent variables would be attendance, high school GPA, and SAT score. So let's say we had a big data set for a bunch of students and we asked the computer to perform the regression for us and it came up with this equation. Well, then we can just use that equation in order to predict the performance of a student. So for example, if we had a student whose attendance was 41, whose high school GPA was 3.4, and whose SAT score was 1200, then we could just plug those numbers into the equation and we would predict that this student has a course average of 82. On the other hand, if we looked at a student who has the same variables except now they have an SAT score of 1400, then we could take those values and plug them into the equation and we would predict that this student would have a course average of 88. So we just looked at an example where we had two identical students, except the first one had an SAT score of 1200 and the second one had an SAT score of 1400. We were able to calculate the first student's course average and we got 82, and then we're able to predict the second student's course average and we got 88. So the difference between the two scores was equal to 6. Now, it turns out that we don't need to actually go through all of those calculations. If we know that two students are exactly the same, but they differ with respect to one variable, then we can actually just take their difference on that one variable and multiply it by the slope for that variable, and that will give us the predicted difference between those two students' output variables. So taking a look at the example we were just looking at, if we assume that two students are the same, except one's SAT score is 200 points higher than the others, and we want to predict the difference in course average, well, we can just take that difference in SAT scores, which is 200, and then we can multiply it by the coefficient on SAT, and if we look in the equation, that coefficient is 0.03. So 200 times 0.03 is 6, and so we would predict that those students have a difference of 6 in their predicted course average. Notice that that's actually the result that we got before. We predicted the first student was 82, the second student was 88. So the difference between those two numbers is 6. So this actually is working out. Here's another example of applying that technique. Let's say that we have two students who are the same except one's high school GPA is 0.7 points higher than the others. What would we predict the difference in course averages to be for these two students? Well, we would just take their difference in high school GPAs, which is 0.7, and we would multiply that by the coefficient for a high school GPA, which is 10. And so 10 times 0.7 is 7. So we would predict that these two students have a difference in course averages of 7 at the end of the semester. Alright, well that actually concludes this supplemental lecture for correlation and regression. This one was pretty short because this was a pretty simple topic. As always, guys, please let me know if you have any questions on anything at all. I'll be happy to help you out. Have a good day, and I'll see you next time.